See, here one more point we can add here, that suppose that if any gas obeys this equation of state, which is equation 3. See, this is equation 3 or equation of state. So obviously if gas obeys this equation of state, so definitely this will obey Boyle's law and Charles' law. So if we say that okay, a gas is obeying Boyle's law and Charles' law both, then the behavior of gas said to be ideal. So we can say that if a gas obeys the Boyle's and Charles' law, the behavior of gas is said to be ideal. Because this equation of state, basically this is the combined gas law, you can say, combined Boyle's and Charles' law. So the behavior of the gas said to be ideal, right? So if we see this equation 3, this is very important equation, PV is equal to nRT. So this equation, I mean the equation of state can be expressed in terms of density as well, right? So equation of state in terms of density, or you can say mass density. So equation of state in terms of mass density. This is very important point. And why I am specifying this mass density, not simply writing the density. There are two types of density we can use here in chemistry. One is mass density and other one is number density. So first I am taking this mass density. After that we will see in terms of this equation of state in terms of number density. So see, PV is equal to nRT. So N is equal to, we can write W by M, correct? N is equal to W by M, where W is the mass of the gas, and M is the molar mass of the gas. Molar mass of the gas, right? So we can write here PV is equal to W by M into RT, or we can write here P into M is equal to dRT. So this is equation 4, right? Where D is here, D is equal to W by V, and it is called mass density. Units could be grams per liter or grams per ml. So as per the requirement, you can interconvert the units. So now we have two crucial equations. One is equation 3. This is what equation 3. So this is equation 3 and this is equation 4. So now we have this equation 3, a very popular equation, or you can say very fundamental equation, PV is equal to nRT, and all formulas we can we can derive from this as well. So this is the equation of state in terms of mass density, right? Now see the beauty of these two equations, that these two equations you can apply on the pure gas as well as gaseous mixture, right? So equation 3 and 4, equation 3 and 4, equation 3 and 4, both can be used for a pure gas or a mixture of gases, right? Now see what different changes in these two equations will takes place when we apply for gaseous mixture. So suppose that if we have uh, two containers, and suppose that here we have taken a pure gas, suppose that helium, and here we have taken helium along with nitrogen. So here we have two gases, helium and nitrogen. So see, suppose that the temperature of this closed system is T, temperature of this system is T, right? Let the volume of this container is V and volume of this container is also V. So if only one gas is here, then what is the pressure of the gas? So pressure of this whole system is equal to, pressure is equal to P, because only one gas is there. What is the V for gases in the equation of state? Basically this is the volume of container. There is no individual volume, there is no volume of gas, every gas occupies the volume of the container. So here volume, basically volume is equal to the volume of container, volume of container, and this is equal to V. What the moles of, because you before applying this PV is equal to nRT, you have to specify all four variables. So moles is equal to, let n moles of helium are there, and temperature is equal to T. So what is the equation? Now the equation is PV is equal to nRT, right? Now the question arises here, that can we apply this PV is equal to nRT to over gaseous mixture, means mixture of helium and nitrogen? The answer is yes. Can we apply this PV is equal to nRT on an individual gas helium in this mixture? Think. I am again repeating the question. Can we apply the equation of state on this gaseous mixture, means mixture of helium and nitrogen? The answer is yes. So my second question is, can we apply this PV is equal to nRT or equation of state on this individual gas helium in the mixture? Means in mixture, can we apply this PV is equal to nRT on the individual gases? The answer is yes. You can apply PV is equal to nRT at each individual gas, whatsoever number of gases are there, and you can apply the PV is equal to nRT on the total gaseous mixture, right? So the first question first I would like to answer or address, can we apply equation of state at the gaseous mixture? So equation of state on gaseous mixture, on gaseous mixture, the answer is yes. Now in place of pressure, what we can take, we can take pressure of mixture, right? Means pressure of helium and pressure of nitrogen, both mixture. And what is the volume? Volume is equal to V. There is no V mixture like anything here in case of gases, because V is the volume of container. So whatsoever the volume is here, that same volume both will occupy the same volume. So here, that's why this is V is the volume of container, not the volume of gas, and this is equal to the volume of gas. You can, if you want, you can write. So there is no V mixture type of any concept, right? So we will write simply, this V, volume of container. What is temperature? T. Temperature is also T. See, when two or more gases or two or more matter were kept in the same system, so it is not possible that helium will bear some other temperature and nitrogen will bear some other temperature. Whole matter will have the same temperature, right? Whole matter will have the same temperature. It is not possible that helium and nitrogen may have different temperature until unless your system is not designed in a such a way that both were kept under a different thermostat. Otherwise it is not possible. This is if this is a homogeneous single system. So temperature is T, right? And what about moles? Yes, moles definitely will change, and this time we will have moles of mixture, N of mixture. And if we talk about density, so in this case, density, so in this case we will write density of mixture. What about molar mass? So in this case we have to write here molar mass of the mixture, right? So in case of mixture, certain properties, certain variables will change and they will have the value of mixture, but certain properties which are not, dependent on the that individual component, like volume and temperature for gases, or temperature for any matter, but for volume and temperature both for gases, then they are same. So now how this equation 3 will be here? P mixture V is equal to N mixture into RT, right? So and P mixture, molar mass of mixture, is equal to D mixture into RT. Equation 4 is like this, and equation 3 is like this, right? Clear to everybody? Okay, good. And here equation 4 is like this, PM is equal to DRT, right? PM is equal to DRT. Okay, now another question. The question is, can we apply this equation of state on the individual gases in the mixture? Can we apply equation of state on helium and nitrogen separately The answer is yes, we can apply. Now what changes will take place? Now see, when we apply on helium, PV is equal to nRT. So this time the pressure of helium, pressure is equal to pressure of helium, right? Volume is equal to V, simply total volume. Temperature is equal to T. As for the mixture, moles is equal to moles of helium, right? So this time, this pressure of helium, this is known as partial pressure. Partial pressure of helium. See, when any property is observed in the mixture, then this is called what? Partial property. So whenever any property you will observe in the mixture, so whenever any property is observed in mixture, then it is known as partial property. So if the pressure is observed between in what mixture, then this is called partial pressure. If volume, so for gases there is no concept of partial volume, but for liquids and other components, solids, you have this concept of partial volume, right? So partial pressure. So what is the equation of state for this? Pressure of helium into V is equal to moles of helium into RT. So this is the equation of state on a single gas in the mixture. Similarly, pressure of nitrogen into V is equal to moles of nitrogen into RT, right? And here P of helium is called partial pressure of helium. and P of N2 is equal to partial pressure of N2, right? Now, see, uh, in this case, can we write this equation? Moles of mixture is equal to moles of helium plus moles of nitrogen. We can write or not? Yes. Total moles of the mixture is equal to moles of helium plus moles of nitrogen. So let the total moles are N. So N is equal to N mixture. So N is equal to, we can write moles of helium plus moles of nitrogen. Right? Or not? Yes, we can write. Now, at this moles of mixture, what we can write here? Moles of mixture is equal to P mixture V by RT. We can very easily write. So, P mixture into V by RT. And this is equal to N of helium. N of helium is equal to P of helium V by RT. P of helium V by RT plus this P of N2 V by RT. So we can write here that this RT cancel, V cancel. So we can write pressure of mixture is equal to partial pressure of helium plus partial pressure of nitrogen. You know, this is, you can say that this is a special form of equation of state, and this is equation A. Let this equation A, and you know, dear students, this equation is known as Dalton's law of partial pressure. Basically, what Dalton suggested, that if we take two or more gases in a same container, and obviously if we have taken same in the same container at the same temperature, so all gases are on the same temperature, volume is same for all the gases. So in that situation, this equation you can write that the total pressure of mixture is equal to the partial pressure of each gas. So under the similar condition of V and T, you can write here that the partial pressure, sum of partial pressure is equal to the pressure of mixture, and this statement is called Dalton's law of partial pressure. So we can write here Dalton's law of partial pressure. Dalton's law of, this is not any special law. This is the extension of this equation of state. How you are manipulating this, right? So partial pressure. So Dalton's law of partial pressure, so you can write here that at constant temperature, total pressure, total pressure of gaseous mixture is equal to the sum of partial pressures of each gas. Gas taken in the same container. Right? So you can write P mixture is equal to sigma of partial pressures. Right? Now you can write this. You have this equation P mixture V is equal to N mixture into RT, and partial pressure of helium is equal to moles of helium into RT by V. So suppose that this is equation X and this is equation Y. So if at any point of time we can divide this equation Y with X, right? This equation divided by this equation. These two equations, how I have written, I am talking about the reference of above example what I have taken. So we can write here pressure of helium divided by total pressure of gaseous mixture is equal to moles of helium divided by moles of mixture, because rest variables are same for both, right? Now see, you can write this. What is this quantity? If you see, this quantity is called mole fraction of helium. So you can write here mole fraction of helium. So this is equation what Z. So you can write here partial pressure of helium is equal to mole fraction of helium, X is the symbol of mole fraction, into total pressure of the mixture. So this is also not any special formula. This is also a manipulated formula and coming from this equation of state. So you can say this is the part of equation of state. No problem. Means your 90% formula, all formulas are derived from this PV is equal to nRT in physical chemistry, right? So similarly, you can write here that the partial pressure of nitrogen is also equal to the mole fraction of nitrogen into total pressure of the mixture. So you can write here that the partial pressure of gas A is equal to mole fraction of gas A into total pressure P mixture. So this is a general formula. So this is what a result of this Dalton's law of partial pressure, right? So some people may argue that this Dalton's law of partial pressure is not applicable in the reacting gaseous mixture. In my opinion, there is no problem. You can apply this equation of state, because if you are talking about Dalton's law of partial pressure, that is not a new equation. That is not a new law. That is simply PV is equal to nRT. So PV is equal to nRT is applicable over the reacting gaseous mixtures as well. See here, I have taken the example in which there is no reaction between these helium and nitrogen. But if you have gases like H2 and O2 which are chemically reactive with each other, then also you can apply PV is equal to nRT. The only requirement to apply PV is equal to nRT that this P, V, N and T should be constant with respect to time. That's it. So obviously before start of reaction, all variables have some value. During the course of reaction, when the dynamics of material is taking place, that some moles are consuming, some are appearing, some are disappearing. So at that moment, moles are changing. So if moles are changing, then more dependent other variables are also changing, like pressure is also changing. Let be volume of container is fixed, temperature is fixed, but no number of moles and pressure are continuously changing. So once the reaction is over, then number of moles are constant, and if number of moles are constant, then pressure is also constant. See, V and T are constant. Number of moles and pressure are varying with time, but once the reaction is over or reaction attains the equilibrium, then you can apply P is equal to nRT, no problem. Because now the moles are constant with respect to the time. So don't worry, you can use this equation of state even a reacting gaseous mixtures as well, right? So another case, can we apply equation of state on reacting gaseous mixture, on reacting gaseous mixture? The answer is yes, but not always, means not at all the time. There is some restriction, but uh, at the answer is yes, but for irreversible reaction, when reaction is over, when reaction is over, and for reversible reactions, at equilibrium. You know, for reversible reaction at equilibrium or for irreversible reaction at equilibrium or irreversible reaction when reaction is over, all variables, all variables, all variables P, V, N, and T are constant, with respect to time. So when all four variables are constant, in that situation you can apply this equation of state. And in the same manner as we have apply this Dalton's law of partial pressure, you can apply in the same manner. So hopefully all of you are clear this diversity of this equation, how and where we can apply this equation, right? Now one more term we can use here, that equation of state in terms of number density. So how to express this equation of state in terms of number density? In place of mass, we can take number. So number density, so see, first we should define what is number density. So number density is equal to number density is equal to number of gas molecules present per unit volume. Per unit volume. So number of gas molecules n divided by V. So this is the number density n by V, where n is not the moles, n is not moles, n is the number of gas molecules, right? So this is called number density. So PV is equal to n into RT. This is equation 3. Now equation 3 is very popular equation, right? Now this n is equal to, we can write n by Na, where n are the number of gas molecules, and Na is the Avogadro's number, Avogadro's constant, right? So we can change here. So we will get PV is equal to n by Na into RT. So we can write here n by V is equal to P into Na by RT, right? So this is equation A, and this is equal to the number density. So sometimes this number density term, this is more important than mass density, because this number density sometimes because sometimes we will deal with the number of gas molecules present per unit volume. So in that case, this is very important term. And in future, in chemical equilibrium and other chapters, this is very, very important. Even in the same chapter, we will use this term. So number density is equal to the number of gas molecules present per unit volume. So sometimes if we observe the properties depends on the number of molecules, so those properties becomes important here. And in that case, we prefer to use number density rather than mass density, right? And unit accordingly you can justify, you can say number per liter, or number of molecules per liter, or per centimeter cube or meter cube, right? So this is the calculation of number density, right? So in this way we have various forms of this equation of state, when and where and how we can use. Now one more question I have, that can we use this equation, another question, can we use equation of state, in open container, open system, right? So the answer is, this time the answer is again yes. What is the problem? See, if you have a open container like this, and if you have some gas here, okay, no problem. And all of you are knowing that this pressure of gas is a potential, so here atmosphere is there. So when you have taken this gas in the container here, so if pressure of this gas is more than the atmospheric pressure, this is the open container, so some gas will escape out. So basically there is a equilibrium here, and pressure always remains same. So for open container, pressure is constant. Pressure of gas is constant always. Don't see that some of gas if escape out, then atmospheric pressure will change. No, 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 no. See, atmosphere is so huge, so large, that a little bit gas if escape out, then the pressure of atmosphere will change. This is not like that. And if we maintain the temperature, then also temperature is also constant. So P and T, no, we can differ this T here. V is also constant. Why? Because for gases, volume is nothing but volume of container. So if rigid container is there, so volume is constant. So P and V are constant. So two variables we can change temperature, right? So now PV is equal to nRT. If P and V are constant, so we can write here N1 T1 is equal to N2 T2. So this is the equation we may use for open containers, where N1 are the moles of gas at temperature T1. And N2 are the moles of gas at temperature T2 in the container, right? In the container. So for open containers, you can use this formula, right? So you can use this equation of state. Some changes will apply. So with those changes you can use, right? Now see, there is one question. Example, basically, an open vessel contains n moles of air at 17 degrees Celsius. So suppose that this is a open vessel. So obviously when n moles of gas are given, so they are in equilibrium, n moles initially given. So n1 is equal to n and t1 is equal to 273 plus 17. This is equal to 290 Kelvin. Now it is heated, so obviously when it is heated, pressure will increase. So pressure will increase, so gas will escape from here, because from high pressure to low pressure gas will move. So some part of air will escape from here. So let N2 is equal to this N dash. This is left uh, moles in the container at temperature T2. T2 is equal to 117 plus 273. This is equal to 390 Kelvin. So at this temperature, N dash moles are left. And here, I mean, N moles were initially present, right? So we can use this N1 T1. So N into 290 is equal to N dash into 390. So N dash is equal to 290 by 390 into N. So this becomes equal to 0.74, 0.74 N, right? So this moves left at 117 degrees Celsius. Hopefully up to this it is clear. Now moles escaped. Moles escaped is equal to initial moles minus moles left. So this is equal to N minus 0.74 N, right? So fraction of mole percent. So mole percent escaped is equal to moles escaped by initial moles into 100. So moles escaped are N minus 0.74 N divided by N. So this we into 100. So this is equal to 1 minus 0.74, approximately point what? 26. Approximate 26% mole percent of gas were expelled out from this container, right? So in this way you can solve this type of problems. See this question. Given it is given relative humidity in a room is 65%. What mass of water vapor is in the air at 25 degrees Celsius? If the room measures this, vapor pressure of water is 23.8 torr at 25 degrees Celsius, right? So first all of you should know what is relative humidity. After that you can calculate the mass of what water, right, present in the air. See, relative humidity is equal to, this is equal to the actual vapor pressure actual vapor pressure of water in air divided by the equilibrium vapor pressure equilibrium vapor pressure at that temperature. Vapor pressure of water at that temperature, right? So see here, the actual vapor pressure of water, it is not given here in this question. Rather, they have given this vapor pressure of water, right? So equilibrium vapor pressure of water means vapor pressure of pure water. That is given is this, and you know one very important point that this vapor pressure or equilibrium, better more scientific and clear word is the equilibrium vapor pressure. Equilibrium vapor pressure of water depends mainly on temperature. What is the meaning of this? The meaning of this is that if you take water here in this container at any temperature T, and see this is in equilibrium in some part of water in the vapor. So this equilibrium vapor pressure, basically it depends only on temperature. Suppose that the whole this container volume is V, and if whole volume is transferred in the 2V container, suppose that 2V container, and keeping the temperature same temperature, so the vapor pressure this time, again suppose that here P, so here also P. Means if you change the volume or if you put some gas here from outside, there is no change in this equilibrium pressure. This is always constant at given temperature. So there are some condition on with, that's why here I have not written only, I have written here mainly. So mainly it depends on mainly, the meaning of mainly is more than 99% cases. There are few cases in which its dependency is some external pressure dependency is there, but normally it is not depends on temperature. Any other factor. This mainly depends on temperature. So if you increase or decrease the volume of container, or if you put some additional gas here, or you put some gas molecules. Suppose that if you pass here some gas molecule, suppose that you are changing 2V volume and pass air here in this, right, some air gas molecule, there is no change in the vapor pressure, right? So vapor pressure of water, which is equilibrium vapor pressure, that mainly depends on temperature. So see here in this question, if you are able to calculate the actual vapor pressure, means actual pressure exerted by the water vapors in the atmosphere, then you are able to calculate the mass of water. So relative humidity is given, so you can write here 65 by 100 is equal to pressure of water in air divided by what? equilibrium vapor pressure, which is given, this is 23.8. So now you have pressure of water in air is equal to 0.65 into 23.8. So this is equal to 15.5 torr. Right? Now you can calculate the moles by using this equation. PV is equal to nRT. So moles of water in air is equal to pressure of water in air multiplied by volume. So all of you are knowing that this volume is same because room dimension is given. I think this is 4 into 4 into 3. So 4 volume of room basically divided by R into T, right? So now put the value here. You have 15.5 torr. So what unit you should use here? Pascal. So 15.5 divided by 760 multiplied by 101,325 Pascal, right? So 101,325 Pascal. So now it is pressure, and volume is 4 into 4 into 3 meter cube divided by, we have to take this R is 8.314 joules per mole per degree Kelvin, and temperature is 298 Kelvin. So from here, if you solve this, you will get 40 moles. 40 moles means in that room, under this situation, what temperature is given, what condition is given, there are 40 moles of water are present in the air. So what mass of water present in the air? So mass of water in air is equal to moles of water into molar mass of water. So this is equal to 40 into 18. So it becomes equal to 720 gram, right? Approximately this is 720 gram. Answer. So in this way, you can calculate how much how much mass of water, what mass of water vapor is present in the air at 25 degree Celsius. So in this way, you can calculate. And remember, this is very important point, that equilibrium vapor pressure, or you can say vapor pressure, mainly depends on temperature. It is independent of the container size, presence of some inert gas, or presence of any other inert gas. Here there is no change in the water vapor pressure, right?